I've improved some notation too. Okay, let's begin. So we were right in the middle of this discussion of stochastic search variable selection. So this is just MCMC using this sort of prior. And there are a zillion SSVS algorithms. So you'll see efficient SSVS and more efficient and even more efficient. They don't name themselves that. I do have my favorites out there if you ever want to discuss what my favorite implementation is. It requires a technique called reversible jump. And in general, I don't like that algorithm. But in the particular case that I'm thinking of, it actually is a pretty good algorithm for moving through things. I want you to explore all these SSVS packages and out there. So on your homework, you have an opportunity to go and experience SSVS algorithms. You can also implement it yourself. But of course, this algorithm requires you to use the Bayes factor, the way I'm writing it down. There are some methods that will come up with very good approximations that they embed into the algorithm. And so how good are the approximations and how well does it work? I always say go do a simulation study to find out for yourself. So I usually don't have the answer in the paper. They'll give you really good news about their algorithm usually. But in this problem that we're dealing with, where we've got a whole bunch of data, it's coming from y is going to be normally distributed, some x betas, and I'm just going to say this is a subset. So some true subset. It's real nice when we tell you which x's to include in the model, but if I don't, then I need to zero a whole bunch of things out. So this will have some zeros in there. So plus, I'll just say with some variance. And you can make this more complicated if you want. So SSVS algorithms, at least the ones that you'll be playing with, have this normal form. The prior looks like that. If I pick the prior to be conjugate, I can work through this integration. If I did something trickier and I didn't make everything conjugate, like I used Val Johnson's priors right here, I wouldn't be able to work through this in closed form. So the non-local thing. All those different things that can matter and are a huge deal. Oh, I picked this also matters. But I can solve these integrals if that's normal right here and I'm using the conjugate form. What will the posterior look like? Effectively, it'll be a point mass mixture prior in a posterior space with an updated expectation and variance. So how do you find those updated expectation and variances? Solve these integrals right here. It's a completing the square activity. So I did spend about 5 minutes looking to see how many times I could find this Bayes factor written down in closed form. And I was able to do it about 5 times online in 5 minutes. So it's in every paper. And so I ask you to work it out. What will this have to do with? How will you know if your solution is correct? Well, you probably go and check it to the literature. I think that's an important skill. But you should realize you're going to be using all the y's. Somehow you're going to be using the x's that are in this model right here, and somehow you're going to treat the x's on the jth model, where I'm trying to zero that thing out, or I should say where beta j is equal to 0, those should come in separately. Shouldn't be treating them the same. So I can look at a mathematical equation and decide if you're handling everything in the compartments compartmentally correct. So which xj's do you use? Which of the columns? Which y's do you use? And I know what the form should look like. So it should probably have some x transpose x's in there and x transpose y's. So things like that should be coming in. This is just a regression problem. And so what I'm encouraging you to do is look for this solution, also try to work it out. You learn the skill to work out this integral in the first couple weeks of class. From that, I can transform my Bayes factor into this posterior probability. So I'm giving myself a little bit of notation. So what this notation is this is model K, whatever it is. Model K is just a bunch of indicators, zeros and ones, telling me which covariates are in or out of the model. This notation says that I'm going to consider this model K right here, but I'm going to delete the jth variable. So that's what this says. So this is model K with M, K, J is equal to 0. So these are just indicators. So I'm taking and I'm removing that out. So that's what my notation is. I have a prior on that. I have a prior on model K. This is just model K, and this is model K removing the jth variable. So I'm calling that Bayes factor model K minus J. So I have to be very clear about this. Somebody gave me this Bayes factor and they said I'm comparing model K to model K with the jth variable removed. I need to know which goes in the numerator and the denominator. So in my class, I always put the reduced model on top. But in half the papers that I looked at and found Bayes factors real quickly, some of them had this thing inverted. So be careful. Read the notation before you code it up. You understand what it means. So that's the Bayes factor we compute right here. So again, this is going to have all of the columns somehow in this Bayes factor, which will be computed. All of the columns in model K will show up in the formula, and somehow you'll be treating the jth column differently as well. That should be clear to you. Okay, so what we do with this is we calculate these probabilities right here. So this is the most basic SSVS algorithm I can think of. And so all I'm going to do is I'm just going to be flipping coins with these probabilities. So I'm going to initialize. So step 0 is going to be initialize our model. I'm just going to call it MT. So I'll call this MT, where T is equal to 0. So maybe that could be the full model. We'll have all the indicators built in. How many indicators? Cap P. So 1 for every column in X. Or maybe I could start with the most reduced model, or maybe I could do this randomly. You guys know that this will all affect your burn-in time. So I select something right here. Eventually, this should converge to the posterior distribution on these model spaces right here. So I've got all these probabilities right here for comparing two models. What I want are these marginal model probabilities. So not just comparing two models, but basically all of the 2 to the cap P models. And so if I run through this algorithm, eventually the occurrence of seeing a particular model will happen with a frequency that's proportional to that probability. That's MCMC in a nutshell. And so what are these probabilities? I just computed them over here. So for your problem, I would probably just let these be half-half, something like that. So every model is equally possible before you run into this. If you want to build in some extra penalties, people do that. So Bayesian model selection procedure, all of them differ in maybe this or how you select these right there. So these probabilities, how you calibrate the alternative prior, there's no real choice here. And the computational algorithm you use to search over everything. And so basically I'm just going to be flipping a Bernoulli with these probabilities. So this one is, if the parameter is already a 1, then I know I'm moving from a 0 to a 1, or a 1 to a 0. And that's that probability that I've written down. So I'm just going to flip a coin with that. If I'm going the other direction, and I don't have the parameter in the model, I'm going from a 0 to a 1, I'm introducing that parameter, the probability is 1 minus that thing. So that's all there is to it. So I just basically, for a model, which is just a vector of zeros and ones, I'm just marching through each element and flipping a coin for it. I just do that over and over again. I do that some large number of times. So, some large number. So I need to make sure this thing converges. It's a little bit hard, but not too hard. So what I probably would do to make sure that this is converging is I'd pick some norms on the model space, the ones and zeros, and just make sure those norms are converging. They make nice fuzzy caterpillars. Or the probability of any particular variable being inside the model, that converges to some nice probability. And all the joints between all the joint model probabilities, all the beta j's, those all converge to something nice. So you should be monitoring every feature you can think of. And that's basically it. So this is how we search over model space. So this is, right here, changing into a 0. This right here is changing into a 1, changing the model. So we could do one other thing. I might be interested in what the actual betas are. I'm not getting them. And so all I would have to do, if I wanted the particular betas, is right at this point right here, I could update those. So we could sample beta j, given everything else. So I could get its posterior distribution on beta j. The way that I wrote it down without putting this in, I've integrated out all beta j's. They're not there. So think of it this way. If I had done the joint updating of model space and beta j's and I threw the beta j's away, they're integrated out of the solution. It's the beauty of MCMC, or any sampling technique. I can just take whatever my columns are and throw them away, and that's marginalization. Okay.
So there is no t-1 in the algorithm, so is it okay?
My apologies, yeah, thank you very much. So at the end of this right here, let's go mt plus 1 is equal to mt. So that's that. So at the end, I just update.
And also, I thought mtj is kind of binomial variable, which is 0 or 1.
Yeah.
But you assign that the probability into mt.
Now that's a Bernoulli coin flip, so I'm sampling. So I'm sampling a Bernoulli.
Okay.
So that's going to be a 1 or a 0 is the way that I mean it. So it's a Bernoulli over that probability. Not plugging in the probability, I'm sampling from a Bernoulli with that probability. Good question.
So, in terms of notation, last time whenever we wrote the models, we wrote like M1 and M2, and then we wrote them, like not in terms of linear algebra, beta 1 times, etc. So here, whenever we say MK, is that kind of interchangeable?
It's just MT right here. So the M is getting updated, right? So it's a random variable.
And what's the difference between beta and MK? So beta is just like the element of a column MK, that's it?
Yeah.
Okay.
So it's just a 1 or a 0 times that coefficient.
A 1 over 0 times that coefficient gives you the MK?
Let's do it this way. So just to be really clear about this. So I could write this down. Xi j. So beta j right here. J goes from 1 to p. And so this could be a 0 or 1 the way that I'm writing it all down. So let's just say this equals this. Xij, and this will be model j right here. So this is going to be a 0 or 1. And I'm going to give you some other name for this. So this right here is a 0 or 1. So these are point mass mixtures. These are continuous variables. And I'm just multiplying in the 0 or 1. What's the probability that these things are 0s or 1s? Right there.
And this beta here that we're trying to sample is the beta tilde, right?
Yeah, that's right. So we'd be getting the beta tilde in this case. Just in or out. It's an indicator. So I multiply by 1 and it keeps everything the same. I multiply by 0, it zeroes everything out. So that's all we're doing.
How do we calculate the Bayes factor? How do we do the integral?
Right.
So do we integral the beta over 1 to 0 to j, or do we?
So this is whatever model this is.
Yeah.
In this model, the way that we're at least choosing to go through things where we just update one variable at a time, this model right here is going to look just like that model, but with the j parameter removed. So if this already has the beta j removed, this ratio is 1, if they're the same models. Or these are off by just one coefficient. How do I do those integrals? Complete the square. Those are normal densities that are in there.
What's the upper limit and lower limit of the integral?
So beta j can be anything.
we integral over each
beta. Yeah, that's what this is writing down. So all of those betas in this model, all of those, there's a lot of cancellation going on. Comparing two models. So just make sure you understand it in your head. What are you comparing? And then the math is just making sure you translate correctly.
So the else statement where m of j is a 0 and it becomes a 1.
That's right.
Now m is a 1, how do we figure out what the beta value is associated with that?
So then I would just sample from its full conditional. So now get beta j given everything else, right? So given that model, that whole model, I just want to update one thing. All right. You know how to do it for full vectors. It's pretty easy when you just do it for a scalar. So this right here is just a scalar right there, and I would probably put a t on here so I can keep track of all those. And so it's just this conjugate calculation. You'll figure out which it is. It's obviously going to have something to do with the x's in the full model, the model that you're sampling from. It's really very simple. So, first 2 weeks of class, we were doing that problem. But that is what it is. So we just sample from it. So you have to figure out what the full conditional is. That's the exercise.
How do we select the variance?
Ah, this thing. Matters, right? So I asked you on your homework to tell me how you tuned it and why you chose it the way that you chose it. It makes a big difference. And I've said a lot of times, and hopefully you can think about this every single time, even if you don't understand the reason, that if you didn't pick that with good reason, I don't care to see your analysis. I don't even want to look at it. So, because it doesn't mean anything to me, because it doesn't mean anything to you. So how would you pick it? I need to know how far away 0 I am before I'm willing to reject it. So what I basically told you is that, you know, the point null p-value, that's an absolute error that we're looking at, and we're trying to decide if it's non-zero. And it always will be. In the Bayesian calculation, everything's a relative thing, and I think everything should be relative. Everything is comparative. So that's how far we need to be in some probabilistic sense from 0 before we're willing to reject it. So you tell me. So people walk into statisticians' offices all the time with this poorly phrased question, which covariates are active? And this is really a scientific question. How far away do you need to be in your discipline before you're willing to reject the null? So how would you do it? Somebody's going to come to you and ask you this. And I'm telling you, there are millions of statisticians all over the planet that are doing this calculation for people and giving them something without addressing that question. And so I don't think it's very meaningful what people are doing. Now, we've talked about it, it's got to be subjective. So you're going to have to do something. How would you do it?
Cost-benefit analysis.
Or
How
maybe
expensive
that.
is it to get that data, and how much does it actually affect the outcome?
So this sounds like a real solution that you're gearing up to, but of course, it all depends, right? I think that that is the answer. It all depends. So how are you going to do it in this sort of setup? I'm just giving you a data set. Now you have to do something, some sort of default. And you need to explain what it all means. Yeah, that's what I would do too. I would standardize my x's, and then I would say, I don't know, if you're a standard error or 2 standard errors away, you're probably going to reject it. Everything's normal, so that would be like 1.96 standard units away, calibrated to n though. So in that Bayesian sort of way. So it wouldn't just be 196 standard units. So probably what I would do is I'd probably pick this to be 1, and I would standardize all of this stuff in here.
What do you mean by that?
Subtract off the mean and divide by the standard error. So it's mean 0, variance 1. Saying that, sometimes I think the variance is a big driver, and I hate doing that. I think the variance has the signal I'm looking for. But I would probably just say, well, this is a mean-based analysis, and I've standardized everything because I don't know what the x's mean. They don't have any real meaning to me, so I'm just going to treat them all the same. Makes sense? That's what they teach a Stat 101 student. So is that the only thing you do? I don't think so. I've done a lot of different things, but I would say without any context into the problem, I would standardize and I'd pick that thing to be 1. Does that make sense? So not the only thing you can do. So again, I hope you do realize there's lots to be considered, and if it bothers you, don't run regression models for people. So I don't feel comfortable with this whole question of asking, what does 0 mean and a non-zero mean? How far away does 0 need to be before I was willing to include it in the model? I'd say just tell people, your clients, when they come in, I don't feel comfortable answering that question. So you won't have a job for long. So, but I wouldn't just say, well, I just do whatever method and I haven't explored them. So this homework will help you to, at least understand what the influences are. You could sit there and make this very, very, very big. What would happen if you made this huge?
Everything would converge.
Converge. Everything's going to converge no matter what. If you get this thing coded up right, that's not a diagnostic into if your model's good. If your MCMC converged, it just means that your algorithm for approximating the solution is finished approximating. So, what happens in the point null case, in the hypothesis test, if I end up making the variances extremely big? This is the Lindley-Bartlett paradox.
Does the probability of any beta j just become equivalent? It's just all over the place. I mean, if the variances are that big,
That is really big.
then any one beta j is as good as another as far as.
No, I don't think so.
The probability of the null goes to 1.
Yeah, the probability of the null starts being 1. So it starts putting infinite support on the null model. So it's going to start zeroing everything out. So if you make this huge, you're going to get very sparse models. So everybody looks at this stuff. The whole question's right there. So this will be your first time really experimenting with it. It's a little bit more difficult than just the sharp null test, but we are just sharp null testing. That's what the Bayesian does. So if you don't like relative answers and comparisons and all of that, do not do analysis for a living. That's how I feel. So everything is analyzed compared to something. Okay, any other questions about this?
Should the probability be 1 minus pi null over pi null? Because that's the...
Oh, yeah, you're right. Absolutely. I did that upside down. Thank you. That's inverted. So that's really what it is. You update who's in, and then you sample the beta j's. Here's one of the beauties. There's code everywhere for this. It's littered everywhere. And so if you're playing around with this and you want to go use some of that code, I would say try and code this thing up and see that your stuff is working. But you should use those facilities. Really good facilities. They'll give you graphics so you can see how often a variable's in and out. So you can kind of look at some graphs to decide which model you want to pick. So if I wanted to answer a question like, what's the importance of the third variable? I just look at how often it comes into the model. And so if it only comes in 3% of the time, I would say the probability of that thing being in is 3%, 0.03. So pretty small. I don't like that parameter. So we make decisions like that. And then you can look at joint assessment, what comes in together. Keep in mind, collinearity will mess everything up in all of that, because you'll have things fluttering in and out of the model. But really, SSVS is pretty simple, so long as you have a computer. Couldn't have done this 20 years ago, really. Maybe just about 20 years ago you could have done it. 30 years ago. I'm getting older.
So we can know,
Used to be 20.
so we can know how often parameter is in or out the model and set the parameter according to that.
That's right.
But we cannot know the specific value of it. Because
That's
every
right. So
time
all
we-
these betas that come in, they might have other covariates behind them. So these betas that you're getting, if you look at them, they're only specific to a particular model, right? Otherwise, if you take your whole collection of betas, they're being smeared across a whole bunch of different models. And those betas might not mean the same thing to us. And so that's right. If you want to look at a particular model, once you have it, posterior probability of this model being true is 0.87. I like it. That'd be a big probability compared to everything else. So if I had 2 to the p possible models and I came in and I said a priori, each one has probability of 1 over 2 to the p, and then a posteriori, the probability of a particular model has probability of 0.87, that's huge. So these sort of thresholds of 0.05 don't mean much to me, especially if I'm comparing things in big model spaces. One of my common questions I get from scientists when I report this sort of thing, and I say, I love this model, it has probability 0.7. They go, what? That's not high. It's like, compared to everything else, it really is. Let's look at the next biggest model in that whole space. It's 0.02. So it's relative to how I feel about all the other models. So again, everything is comparative. I think so. So that's why people like Bayes factors, because they're showing you that posterior ratio divided by the prior odds. That's another way of interpreting that. So this is how your posterior odds increases over your prior odds. That's what the Bayes factor is showing you. And so it's a comparative thing.
What if the likelihood is misspecified? I mean,
Yeah. So
where is the misspecification of testing the model missing?
yeah, who knows, right? But it depends on the level of misspecification. So let's say I said that this was normal and it was really T4. Keep in mind that error specification in the tails should cancel each other in the alternative and in the null. So in the comparison between models, you hope that you have some cancellation. Of course, if you wildly when you wildly misspecify things, I don't know what happens. So a lot of papers have been written on contaminated models. Bayes usually holds up way better than the classical stuff. Because classical stuff will start saying p-value is 0 on everything, close to 0. But the Bayes thing is relative. So model misspecification, I would argue every time we do an analysis, we're doing something under model misspecification. And so if you are worried about something, how it impacts stuff, Andy, what would I say to do?
A simulation.
Yes. Go and simulate how well it works under that misspecification. So, but there's an infinite number of answers to that question. Could work well, might not work well. I do think in the Bayes cases, if the misspecification cancels well, then you're probably okay. Probably work okay. You could do this, right? You could say, you could run your code, you could code it all up assuming normal, and then why don't you just go and generate your own data with Cauchy Bayes and stuff like that? And then go run your procedure and see how well it works. It won't work better. If it does, you have a bug. What other questions? So, okay. Let's talk about something you can do with this, Bayesian model averaging. So you asked a very pertinent question because you kind of notice these betas that I'm getting are coming out of totally different models and stuff. So what are those betas? Well, they're not quite something you want to use. So I have a scheme where the betas you get are Bayesian model average betas. So that paper I showed you the other day has all that built into it. But here's BMA. Rid of this. So after people did this, they figured out this is a neat averaging tool. So note, SSDS gives you probability of particular models. I'll just write it down, model K, given X and Y. Say I throw away all my betas. The betas are useful for interpreting like a coefficient. But other than that, the betas aren't very useful to you. And so we're getting these things. So out of this algorithm, I could keep the betas or throw them away. I'm getting a whole bunch of models. Once it converges, I have frequencies of models. And I can use those posterior model frequencies to approximate this. So how do we do it? I just look at the indicator function that MT, where did I write this? MT is equal to MK. And then I'll end up looking at 1 over T of these. So I'll assume we've burned in. So maybe I want to go, T goes from cap D, this is my burn-in, and then I've got cap T minus B. Right here. And so I've got 1 over T minus B. That I'm just averaging up. So I'm just counting, so this is posterior model frequency. Frequency of seeing MK. So Bayesians are kind of frequentists, right? We use our MCMC in very frequentist ways. It's an iterative algorithm. I control the frequency. I like that. So this is what you get from SSVS. So the betas can be used for interpreting something, but a lot of times we have misspecified model. So a lot of times, why do we write this down? Why do we say we're looking for a model that looks like this? Y is equal to X beta plus error. We love doing this. Why do we do it?
We can solve a closed form.
Can solve closed form. That's one reason. So let me just ask this question. So why do you like linear models? And the other day I said semi-linear, where I can take some functions, but it's still a linear combination between that function and the beta. And so, why do we like linear models? So, computable. And sometimes you can have closed forms. Okay, I guess that's cool. So when I run this whole thing and I find the subset, obviously I don't have a closed form solution to finding the subset. But at the end of it, once I have a subset that I like, and I say it's these 5 variables that are driving the whole thing, let's just say I know that. And I'll condition on that, and then I get solutions that look like that. Closed form. So that's kind of nice. I can give you a closed form solution to any problem you want right now. Want one? 7. So not a good solution to a lot of problems. Great solution when the answer is 7. So closed forms, useful. Why else do we like it?
Because it's easy to draw insights from linear models.
They're interpretable, right? It's additive. I know the effects. I add this every other thing in, and it soaks up a little bit more residual variance. So it's on an additive scale. I like that. I know how to add things together. I know how to isolate things. If the x's are orthogonal, then I know that the x's are explaining something that's different from another x, i.e. they're independent of each other. So I've got all of that sort of interpretability, and I've got closed form solutions. And I can compute it fast, or at least I can get the computing done. And so I think those are probably 3 reasons. That's all very nice, but we do this for us. And so nobody says nature is being controlled by this. So this is just a statistical model. And we start to understand what are the statistical properties of our inferences. But I would probably argue that in the vast majority of settings where people are using this linear model, that's not actually what generated the data. It's something wildly more complicated, but we can probably carve out most of the signal from this sort of framework, and it's interpretable. So I think people know that this isn't right, and so what people do when things are wrong, and they want to get a better handle on the signal, we usually average. So it drops down all our errors. So we've got error in our model as well. And so to predict well, here's a solution for you, average. That's all I'll mention, if you want to predict well, you should average.
But what if the goal of your analysis doesn't care about averages, then this is not relevant to you?
So it depends on your goal. So I'm saying my goal is to predict. So I've already said what my goal is. So all that meaningful stuff that you use for interpretation, things that mean stuff in your field, I don't care. I just want to forecast.
Oh, okay.
So this is incredibly important. So I just want to forecast something. I don't care about interpreting the model. A few models together. So if you've ever played around in large-scale data analytics competitions, you're going to always kick yourself if you didn't average your solutions. So I'd say if you and your teammate have two different models, they're off by a little bit, and you're discussing which one do you use, average them together. Which averaging mechanism should you use? That's the question. How do you average? What are the weights on everything? And that's what this helps to answer. So this is just forecasting. Very different from inference. But this is how a Bayesian does it. This is BMA. So we end up looking at whatever your model is. I'm going to say Fy. So this is the stuff you want to forecast, given my x's and my particular model. Model K. And I want to look at some number of models. So what am I going to average them with? This is BMA. So I've got those probabilities. I just use them to average over these things. So this might be a linear regression model that's fit a particular way. Normally what you would get is you get y hat out of this thing. You just say that's my prediction, and you put some variance over it. But here's a mixture representation of these models. What are the weights? Bayesian says to use that. That's it. That's BMA. Of course, how you compute this effectively, that's a whole different conversation. That's probably a week's worth of lectures at minimum. So saying that, you could, in spirit, go and run the SSVS thing for a long time, get those posterior model probabilities, and just plug them in right there. So nobody does that exactly. It's a little bit more automated how things happen. So I will say something that I found fascinating about this. So I might say, why? This is going to be my predicted thing. It's coming from this. Gelman says not to do this. Just saw this about a couple years ago. I just thought this was the thing to do, and this is what everybody wants to do. And it does pretty good. So Bayesians are good averagers. So we average over uncertainties. We put posterior distributions on anything we don't know. We measure all that stuff from basically the connections between parameters and data through the likelihood function. Likelihood function is supposed to have all the info out there, presumably. So this is a presumption. Gelman says to do this. K equals to 1 to count K. Fx, Fy, given x, and whatever my model is, but he has different weights. And I'm just going to write them down like this. Pi k, and I'll tell you what Gelman uses for those. So he normalizes everything. But he doesn't do anything Bayesian on this anymore, and he's an ardent Bayesian. So I thought this was kind of fascinating. So what Gelman has told us to do in the last couple of years, and he has a bunch of examples on all of this. I haven't checked it out myself, but he says, why don't you just for each model K cross-validate that thing? Come up with your favorite cross-validation measure, maybe MSE or something like that, and make these things proportional to that. So Gelman says this. Pi k be proportional to some cross-validated metric. Okay, you can pick a lot of different metrics, maybe MSE, absolute error, something like that. And so, and just normalize all those things and treat them as probabilities. So he says, just forget about the whole Bayesian thing right here. Do something totally, where it's totally unclear what you're doing. So why would this maybe work? Here's what I'll help you with. It doesn't really work if the model's true. If the model's correct, the Bayesian has everything written down. They know the whole entire probability structure of everything. And so this right here is kind of assuming that your likelihood doesn't have information in it. It's missing some of the info. You wrote down wrong model. And so you should use some extraneous metric to try to gauge how well you're doing in everything. So all of your modeling assumption is built in right here. In the Bayesian framework, that modeling assumption is built in here as well. We used all that when we worked through our Bayes factors. What Gelman says to do using a cross-validated thing is he's saying, forget about the likelihood. Let's assume that it doesn't have information and penalize with respect to whatever it gets wrong in its prediction. So these cross-validated metrics are always predictive quantities. So I pull some subset of the data out, I look at everything, I see how well I do. If I'm not doing very well, downweight your model. And so it's kind of a neat idea. I just want to throw it out there because I used to think this was unbeatable. But it really goes back to the question, if you've misparameterized, misspecified your model in all kinds of ways, then you probably want your weights to account for that. And the Bayesian thing doesn't do that. I think it's a good starting point. So what would I actually do these days? If I were doing this problem, I'd probably check out both and compare them to each other. And so I think that that's all very reasonable. So that's BMA in a nutshell. What questions do you have? Anything else?
This feels a little bit like double dipping to me.
It
Every
is.
data.
Yeah, it kind of is, right? Yeah, that is a double dip. So, yeah, it's kind of weird. Like, what the heck is this thing?
Yeah.
You've violated all kinds of statistical principles. And so kind of the aesthetics of doing that right there don't seem right to me. And so, oh boy, we're violating all kinds of probability theory, likelihood principle all at once. But if it works, it's kind of cool. So I guess I just want to say, while the BMA solution is cool and good, and I've used it lots of times, there might be something more out there. And so breaking the rigid framework of Bayes and violating the likelihood principle, maybe it's worth doing, especially if your likelihood's misspecified. So, I don't know, you kind of have to use something that's not in the likelihood, right? You have to like fit it, see how well it works, and then, you know, look at those residuals and penalize according to them. It's almost like reinforcement learning, but there's only one round that happens here. So I don't know what to say other than I was surprised to see that the solutions were kind of good. And I trust Gelman. So I don't think I need to go through all of his results and figure out where he made a mistake, because he probably got it right. JD?
For doing cross-validation, isn't pi k essentially just the probability of mk given some subset of x and y?
You could do that if you wanted to. That's why I said some metric. There's a whole bunch of them that can be introduced. So I might look at residuals and penalize according to the inverse of those residuals, something like that. But if you wanted to make it more model-based, that would be different. But maybe that's what you could use. So lots of possibilities there. So if we're being heuristic about it, let's just consider everything that we could do. So this is just an idea and something for you guys to think about. So I don't know, you know, I start to see that maybe Jack was right all along. So he always talked about the Bayes, non-Bayes compromise. Bayesian structure and Bayesian asymptotics are good. They control for n just right, but you don't always want to be a Bayesian. This whole procedure is pretty hard because I have to get all those model probabilities and jump and make sure that I've explored all the models. So this thing that Gelman's talking about is pretty easy. I can run it in parallel too for all my different cross-validated metrics and get all those pi k's in parallel. So I just have this specified model and I just look at its cross-validated metric. I can do that, the thing in the bottom, probably in about 10 seconds, where the thing on top would take me hours. That's the reality of it.
So how to find those models to average?
Yeah, that's a good question. So I would say entertain everything that you want to entertain. So maybe in this case right here, obviously in this case that question is easy to answer. So stuff with high probability. So I would probably, what a Bayesian might say is the full answer is do this to 2 to the p. And all the small probability stuff just doesn't have much of an impact, but you're summing it up and you have to calculate over it. So probably threshold that is what people do in practice. This right here, it's not entirely clear because I didn't run this thing first to figure out which models I want. So you'll have to ask Gelman which models, but I think you just throw down a whole bunch of models. Beauty of averaging is you can throw down a whole bunch of junk and still do well on average. It's fascinating. So it's true, like if you take a machine learning class and you use really clumsy models that have like a 99% error rate, and you average them all together in just the right way, you can bring your error rates down to like 1%. You can completely flip everything.
They're all wrong in different ways.
And you figure out how to penalize them in particular ways. It's kind of neat.
So does it make sense to find the models that you like with high probability, but then average them using Gelman's scheme?
I think so. So I think that sounds pretty good. And I think that's what Gelman did, is he ran some Bayesian things to figure out which models he liked, threw them down, so he had a search procedure, and then he penalized using some out of likelihood metrics. So yeah. So it's like the Wild West nowadays. So we don't have to have any principles in all of this. I'm more interested in how things work. I think Bayes gives us the right framework, gives us some tools, but sometimes it can be pretty cumbersome. So we've got only one more day left. I think I'm going to leave the model selection discussion as it is, but obviously lots to talk about, all the different ways you can specify the alternative priors, so on and so forth. And now we've got Gelman's thing to throw into the mix. It seems reasonable what Gelman's talking about. But we've got one more day. So what do you guys want to do? I figured we could do Dirichlet processes,
Yes.
or we could do reference priors, or we could do something else. DPs, okay, it is. So we'll do DPs next time, and it's actually one of the easier things that I can talk about. Let me tell you what it is in 30 seconds. So still have 2 minutes. I'll let you go a little bit earlier. You write down for a whole bunch of different clusters. So it's a clustering algorithm where you don't know how many clusters there are. So you want your algorithm to adapt to the right number of clusters. And so what you do is for every cluster, so you initialize something into some number of clusters. For each one of those clusters, you work out the posterior predictive distribution. And you're going to take a point out of the data set, run the posterior predictives for every clusters that are left, and then I'm going to compare, and I'm going to look at that one data point and see how well it conforms to the posterior predictive distribution. And I'm going to leave one other possibility, that it doesn't look like any of them, and it looks like something else. And I'll tell you how we average over that next time. But that's really it. If you know about posterior predictive distributions, and you can work them out in closed form, there's a little bit of a catch there, but I'll show you the version where you don't have to work it out in closed form. So basically, you just take a point, you compare it to a whole bunch of posterior predictive densities, see which one is big. It probably wants to go there, but you want to consider another option that none of them look that good. I'll show you how you compute the new possibility of a new cluster. So it should take about 15 minutes and we'll close out. Last bit, review session. So you guys want Wednesday? So 6:30? Or do you guys want Thursday? Okay. Wednesday night, we'll do a review session at 6:30. I'll send out a reminder note. Let's do 2 things. Whatever homework questions you guys have, or whatever you guys want to talk about, and then let's proceed by doing yes, no, maybes after that. So we'll do both. So it'll take about an hour and a half. Or it'll be really quick, depending on how many questions you guys have. That's it. Thanks, you guys.